Hey there, Keys Precalculus. This video is going to go over the last few examples in section 11.3 of your book. And section 11.3 covers how to find the slope of the graph of any function and also how to use that to find the derivative of a function. Now, we're doing this in the same way that we learned in our last class and that we learned in class today. We're doing it using the difference quotient. The only thing different about today is we derived the difference quotient. We figured out where it came from using tangent lines and secant lines with the graph. I'm not going to go over that again. I pointed you to another video that someone else made that's very, very clear. And if you need to refresh yourself on that, you can follow the link to that in the Canvas assignment. But also, what we did in class today was really no different than what we did in class on Tuesday. So you haven't learned any different processes. We're just going deeper into this process. But I still wanted to go over the last few examples with you so that the process is clear. And I just wanted to take a little bit more time to do it here so you could rewind if you need to, and so you can practice on your own. So even though we did example 5 on page 767 in your book, I want to go ahead and go over this one again with you. We didn't actually write it out. We just talked about it in class, so I'd like to write it out here. It says, find the formula for the slope of the graph of f of x equals x squared plus 1. And what is the slope at the points -1, 2, and 2, 1? 2, 5, sorry. So we are going to find the slope of the graph of this parabola. So we know this is the graph of a parabola, and we know that the slope of this parabola changes. We can find the slope at any point if we can find the slope of the tangent line at any point. But you can see tangent lines change, and we talked about that in class 2. Well, how are we going to find that slope? We're going to find a general equation for the slope of any point. Well, we're going to find it using the difference quotient. I'm not going to rederive it for you because, again, y'all learned, we did that in class, and I gave you a video that could help you with it. But here it is again. Here's the difference quotient. And basically, we're finding when it says the m, that's slope of a secant line, we're finding the limit as that secant line's slope approaches the same slope of the tangent lines. In other words, the difference between the slopes of those two lines become 0 or approach 0. So it's basically the change in x's over the change in y's. We are going to use that to find a general formula or equation for the slope of this function x squared plus 1. So in order to do that, we need to first figure out what f of x plus h is. I like to write it down so it's clear, so I don't mess up later. So what is x plus h? Well, all we're doing is evaluating f of x at the point x plus h. So I plug in an x plus h for every x I see. So x plus h, that goes in for that x right there, it's squared, plus 1. That's all I do. And now I'm going to use this difference quotient to find my slope of the graph x squared plus 1. Okay, so I'm going to say my slope is f of x plus h, and f of x plus h is x plus h squared plus 1. I'm going to substitute that in for this f of x plus h. And now I'm going to subtract f of x, which is x squared plus 1. I put that in parentheses so I don't forget to distribute my negative sign. All of it over h. And now I'm going to simplify. Okay, so first I'm going to square the green. So that's x times x is x squared. xh plus xh is 2 xh. And then h times h is h squared. Plus 1. And I'm going to distribute my negative. Minus x squared minus 1. All of it over h. Now I'm going to simplify. I'll use another color so I can cross out the things that are the same. So x squared and a negative x squared here on my numerator cross each other out, cancel each other out. Okay. And positive 1 and negative 1 also cancel each other out. So I'm left with 2xh plus h squared over h. So let's go ahead and simplify this. I can factor out an h from the terms of the numerator. So when I do that, I am left with 2x plus h on the inside. And then I have an h on the denominator. I can go ahead and cancel these common factors of h and h. So the slope is going to 2x plus h. H cannot equal 0 because it was originally on the denominator. I have to show that it can't be 0 because my denominator cannot be 0, because this bottom function here is derived from this top function by using the difference quotient. Okay, now the limit as h approaches 0. So the limit as h approaches 0 of this derived function is going to just be 2x, because when I plug in 0 for h, because remember, I can find the limit of a function even if it's not defined at that point. But I can find the limit at that point. So my limit is 2x. So this really, 2x is the slope of the graph x squared plus 1. And it says to find what the slope is at these 2 points. I can find the slope at negative 1, 2 and at 2, 5. And the way I do that is I just plug in my x values at those 2 points. So at the slope at the point negative 1, 2, I would just, so I say slope at the point negative 1, 2 is equal to 2 times negative 1, which is equal to negative 2. And the slope at the point 2, 5 on this parabola is 2 times the x value of 2, which is equal to 4. So I can find the slope at any point on this graph by using the formula 2x that I derived using the difference quotient. Now you notice that I used the word derive. This equation of a slope, or the slope of the graph, right here that I circled in red, is derived using the limit process from the equation of this parabola. Okay, so I'm going to just reread the top of page 768 to you and hope that this is clear as I read it. In example 5, you started with the function f of x equals x squared plus 1 and used the limit process to derive another function, m equals 2x. This second function represents the slope of the graph of the first function at any point x, f of x. Okay, so any point on this green graph up here, which was represented by f of x, the slope of that function, the slope, yes, of the function at that point can be figured out from the derived equation 2x. The derived function is called the derivative of f at x and is denoted by this, f prime x. When you see f prime x, that means you want to find the derivative. And how do you find the derivative of a function? Well, the definition is on the top of page 768, but it's the same thing that we've been doing the past couple sessions in class. F of x, the derivative of a function f at x, is the limit as h approaches 0 of f of x plus h minus f of x all over h. So basically, the derivative is the limit as h approaches 0 of the difference quotient. Okay? So you're really not doing anything different or new. Let's go ahead and practice using this when they say find the derivative of a function. And we're going to do a couple examples. You're going to do one on your own, and then we're going to talk about a shortcut for it. Because this can get a little tedious. This can open yourself up to mistakes if you're not careful. Example 6 says find the derivative of f of x equals 3x squared minus 2x. So in other words, we need to find this derivative. So I wrote out the problem, and I wrote out find f prime of x, which means find the derivative of f of x. And we're going to do that using this difference quotient here. So the first thing I want to do is find out what my f of x plus h is. So remember, I'm just plugging x plus h in for every x in my equation. So I'm going to get 3 times x plus h squared minus 2 times x plus h. Because again, I've substituted x plus h for every x I see. And so now that I have my f of x and I have my f of x plus h, I can find the derivative. So here, my derivative of f of x is the limit as h approaches 0 of f of x plus h, which is 3 times x plus h squared minus, I'm going to go ahead and distribute my 2, so it's going to be minus 2x minus 2h. Hopefully that will simplify the process a little bit. Minus my f of x, which is the blue one over here. So let's change my color here and write minus 3x squared minus 2x. And then all of this is going to be over h. So I'm going to go ahead and simplify out what I can. I think I'm just going to use one color though here. I'm going to FOIL the x plus h squared, or x plus h times x plus h, and distribute the 3 at the same time. So when I do that, I'm going to get 3x squared, because x times x is x squared, times 3 is 3, plus 6xh, because x times h plus x times h is 2xh, times 3 is 6, and then plus 3h squared, minus 2x, minus 2h, and now I'm going to distribute this negative to the blue part of the equation. So I'm going to get minus 3x squared plus 2x. And this whole quantity is going to be over h. Okay, now I'm going to simplify this by canceling out terms that cancel each other out. So 3x squared plus a negative 3x squared is 0. So I can cancel those. And negative 2x here plus 2x also equals 0. So all I'm left with are 3 terms. 6xh, 3h squared, and negative 2h. So I'm going to rewrite those here. So f prime of x is the limit as h approaches 0 of 6xh plus 3h squared minus 2h all over h. But I've also got a common factor in every term of the numerator, so I can factor that out. And when I do that, I get the limit as h approaches 0 of h times 6x plus 3h minus 2 all over h. And here, these h's cancel. So now my limit, oh goodness, I didn't mean to erase that. Sorry about that. My limit as h approaches 0 of 6x plus 3h minus 2. Well, if I plug in a 0 for every h, my limit is going to be 6x minus 2. And that is the derivative. That is f prime of x. Because that is the equation that I derived from f of x using limits, using the difference quotient, or the properties of limits. And that is also the slope of the equation for a slope of every point on this parabola f of x, or 3f of x equals 3x squared minus 2x. Now before we go on, in this purple box, I'm going to show you other notations for f prime of x. They all mean find the derivative of f of x. This is at the bottom of page 768 in your book. But you can see that it's dx over, excuse me, I did that wrong. It's dy over dx. So let me erase that. Sorry, it's dy over dx. That's one notation. Another notation is y prime. Another notation is d over dx of f of x, which really is the same thing as the dy over dx, because f of x is just representing y. Or you could take the capital D, derivative, sub x, brackets y. Okay, so those are all different notations that mean the derivative of f at x. Okay, so I'm going to put a box around each one. That's 5 different ways to find a derivative. All right, so you may see them any of these ways. These are the most common forms. Okay, I would like for you to find the derivative of f of x equals x to the third plus 5. I would like for you to do this on your own, so you need to pause the video, do your work, and then come back here and check it against mine. So go ahead and pause your video now and do the work. Okay, here it is all worked out. I'd like you to pause the video again, compare what you did with what I did. I hope you got the same answer, but if you didn't, see if you can find your mistake. Okay, so go ahead and pause the video and see if you can, or not see if you can, pause the video and compare. Check your work. Okay, now we're going to do example 7 on page 769. It says find f prime of x, or the derivative of f of x, where f of x equals the square root of x, and then find the slope at the points 1, 1, and 4, 2. So we're going to go ahead and do that. And the first thing I'm going to do is find f of x plus h, which is the same thing as saying the square root of x plus h. And now I'll go ahead and do my derivative. And we do that by taking the limit as h approaches 0 of the f of x plus h, which is just the square root of x plus h, minus f of x, which is just the square root of x, all over h. Okay? And so when I can't just simplify this out. There's nothing I can pull out yet. So I'm going to have to multiply by the conjugate of the numerator. I'm going to have to multiply by 1, so I've got to write it, the conjugate of the numerator, over the conjugate of the numerator, which is going to be, I'm just going to do it in red here, x plus h plus the square root of x. And I'm going to put the same thing on the denominator, so it's like multiplying it by 1. Okay, so now when I simplify the numerator, I can just, this is the difference of two squares, so it's basically just square of the first minus the square of the second. Or this answer is going to be the difference of two squares. So it's just x plus h minus x, that's my numerator, and my denominator when I multiply it out is h times the square root of x plus h plus the square root of x now. Okay, so that's going to help me not have zeros. Now, I can simplify this by subtracting the x's from each other on the numerator, and I'm left with just an h on the numerator over h times the square root of x plus h plus the square root of x. And now I can cancel my h's because they divide each other out. So the limit as h approaches 0 of 1 over square root of x plus h plus the square root of x is, when I just substitute a 0 in for the h right here, it becomes 1 over the square root of x plus the square root of x, which is the same thing as saying 1 over 2 times the square root of x. Now, I can leave it in this form. That's the derivative. I can leave it in this form, or I can simplify it by multiplying both the numerator and the denominator by the square root of x, but to get rid of the radical off the denominator, but I'm not going to do that. Okay, it's okay at this point in time to leave it in this form. So this is the derivative. This equals f prime x. Now it says to find the slope at the points 1, 1, and 4, 2. Well, you just go back to what we were doing before. You just substitute the x value 1 in, and then the x value 4 in to find the slopes at that point. So the slope at the point 1, 1, the slope at that point is just 1 over 2 times the square root of 1, which is 1/2. And the slope at the point 4, 2 is 1 over 2 times the square root of 4, which is 1 over 2 times 2, which is 1/4. So you've got these two different slopes. And if you were to graph it and study the graph carefully, you would see that tangent lines at those points would have that slope. Okay, so that is how you find a derivative. It's no different than what you've been doing already, but now you know that this is the purpose of doing it. I do want to do one more thing with you. I want you to see if you can figure out the shortcut. And what I mean the shortcut of finding a derivative. Okay, so what I did is I wrote up the solutions to all of our examples, and then I wrote an extra example up here. So the red one, when f of x equals x squared plus 1, the derivative of the derivative of x, or f prime x, is 2x. The green, when f of x is 3x squared minus 2x, f prime x is 6x minus 2. Blue, when f of x equals x to the third plus 5, f prime x, is 3x squared. I don't know what color that is, purplish, light purple, magenta. When f of x equals the square root of x, f prime of x equals 1 over 2 times the square root of x, or to help you see the pattern, I rewrote it as 1/2 times x raised to the negative 1/2. And then the extra example I gave you was maybe to help you find the pattern here. So it's darker purple. When f of x equals 2x to the fourth minus 5x to the third plus 3x squared minus x plus 2, the derivative is 8x to the third minus 15x squared plus 6x minus 1. That would be a bear to derive using the limit. So hopefully you can figure out the shortcut. So what I'd like you to do is pause the video and see if you can find the pattern for this shortcut to finding derivatives. And then once you think you figured it out, come back and we'll talk about it. Okay, did y'all figure it out? Well, here it is. When you're given the equation like this one, x squared plus 1, I just take the exponent and I multiply it by the coefficient of that variable. And so 2 times 1 gives me 2. And then I reduce the exponent by 1. So 2 minus 1 is 1. So this first term becomes 2x raised to the first power, because 2 times 1 is 1 and 2 minus 1 is 1. And then here, on the second part of it, there's an understood x to the 0, because x to the 0 is 1, right? And 0 times 1 is 0, and 0, it doesn't matter what that is, because this is 0. It zeroes it out. So basically, if I've got a constant, that becomes 0. It becomes nothing, and I don't have to write it. So let's see if that holds true with this one. Can I say 2, and I multiply it by 3 to get 6 here? And then I say 2 minus 1 is 1. Now here, this is a 1. And 1 times 2 is 2. But 1 minus 1 is 0, and x to the 0 is just 1. So the derivative here is 6x minus 2. Same thing here on the blue one. I take this 3, and I multiply it by the coefficient of 1. So that becomes this 3 here. And then I say the exponent of 3 minus 1 is 2, so that becomes 2. And this is a constant, so it zeroes out. Now this one is a little trickier. This is the same thing as saying x to the 1/2. So I take 1/2 and I multiply it by the coefficient of 1. So that gives me the 1/2 here. And then 1/2 minus 1 is a negative 1/2. So that's written this way to show exactly how it is, how the derivative works, but you can also write it like that, the way we derived it. So if you go through and do this last example, you can follow the same process. In fact, I'd like you to derive this one yourself. So ignore my answer that I gave you and see if you can pause the video, derive it yourself, then come back and see if it's the same. Okay, let's see if we can do this together. So 4, I take this exponent and I multiply it by the coefficient. 4 times 2 is 8. So that gives me the coefficient of 8, and then 4 minus 1 is 3. So that's my first term, 8x minus 3. Then I come over here to my second term, and I say 3 times negative 5, which gives me negative 15. So that gives me my next coefficient. And 3 minus 1 is 2. So that gives me my second term of my derivative. Now for my third term. 2 times 3 is 6. So that gives me the 6, the coefficient of 6, and 2 minus 1 is 1. So that gives me an exponent of 1, which I don't need to show. That gives me my third term. Now let's look at the fourth one. This is a 1 here. It's understood. 1 times negative 1 gives me negative 1, which I have to write because it's not just a placeholder. It's an actual number. And then 1 minus 1 is 0. I don't have to write x to the 0. That's just a 1. That is understood. That gives me my fourth term. And my last term here, this 2, is a constant. And that constant's going to zero out because that's really saying 2 times x to the 0. And when I say 0 times 2, it gives me 0. And I don't have to write that either. So that's the shortcut to finding derivatives. You've done all the hard work, but and I want you to go ahead and practice doing some of your homework problems, doing it the way that we did it before, using limits. But there's a couple of problems that it's kind of hard to do that with. So go ahead and take the shortcut, see if you can get the answer. And I did change the assignment from the original that I had posted before. The new one, which is basically just a change of a problem and then making one of the problems a bonus, is on Canvas. I hope you'll have a great weekend, and I will see you Tuesday.